Namaste, this is Kunal Mehta from Make Me Scientific, and in this video lecture we are going to discuss about the resistances, factors affecting the resistances, and how does resistance vary with different substances. So I'm going to divide this video lecture into few parts. In this lecture I'm going to cover the cause of resistance, formula for resistance, factors affecting resistance, as well as a few of the numericals related to the resistance which is given in the ICSE textbook. So first of all, there are two definitions which are given in the ICSE textbooks about the resistance. Please understand that this is a very general discussion. Even the grade 12 students can also understand from this lecture, but this is for standard 10 students. Okay, so the obstruction offered to the flow of current by the conductor is known as resistance, and the second definition is going to be little bit difficult for you to understand unless you understand the Ohm's law. So I'm not going to discuss that right now. But now you consider that this is a wire or a conductor. Correct? Now this conductor, it is made up of atoms, and we know that atoms, they have a nucleus at its center, and then there are electrons which are encircling them in different orbits. So these are all the electrons in different orbits. Now let me call this as the orbit number 1 and orbit number 2, and this is the outermost orbit or the valence orbit, valence shell you may also say. Now since the electron in the valence orbit, it is very far away from the nucleus, so what is going to happen? The force of attraction between the electron as well as this nucleus is going to be very little. So this electron in the outermost orbit is actually very loosely attached with the nucleus or the atom, so this can be detached very easily from the atom. Second thing you are going to learn in the upcoming classes when you will learn chemistry in detail about Bohr's model, that Bohr's model says that the electron, as they go far away from the nucleus, their energy increases. So energy of the electron in last orbit is way larger than the electron's energy in the first orbit. Okay. Now these electrons, after absorbing little bit energy in form of heat and light from the atmosphere, they jump out of the atom. So when they leave the atom becomes positively charged ion, and those electrons which they leave the atom are known as free electron. Now these free electrons, they are negatively charged and they can roam anywhere in the premises of the given rod or the conductor. Correct? So what's going to be the picture of the conductor that we are going to assume over here? Or the rod is made up of lots and lots of positive ions and lots of free electrons. So please do understand that this rod was made up of large number of atoms, but each of the atom has lost one electron or more than that from the outermost orbit. Please understand, this is the case only with the conductors. We are not going to discuss in this lecture about the insulators as well as the semiconductors. Here we are discussing everything with respect to conductors. So if each of the atom loses one electron or more than that, then there are lots and lots of free electrons which keep on moving in random direction like this. All these free electrons, they are moving in all different directions without any kind of proper directions or random motion of these free electrons. Correct? Now these random motion of electrons do not cause electric current in the wire. So as of now, right now we can say that the electrons, since they are moving in random direction, the electric current does not exist in the wire. Correct? But please understand one more thing, that these positive ions, they are very heavy, so they don't move at all. They are immobile. So before 1897, everybody used to think that the free ions are responsible for the electric current, the positive ions. But after the discovery of electron in 1897 by J.J. Thomson, everybody understood that the electrons, the free electrons, are responsible for the electric current, right? Now, what is going to happen is, if you look carefully, that these free electrons, since they are all moving in different directions, we want them to move in one direction to cause the electric current. So previously all electrons were in different random direction, their motion was in different directions. Now we are going to make them to flow in one direction. So how can that be done? By attaching a battery or creating a potential difference across both the ends of the conductor. So I'm going to call this as end A and this is end B, and I'm going to connect this with a battery like this. Now end B, since it is connected with the negative terminal, that end will become negative and end A will become positive as it is connected with the positive terminal of the battery. The longer one is positive, the shorter one negative. Now if we assume only one electron and analyze its motion. Let's look at that. So now this free electron wants to drift towards the positive terminal of the battery. So this positive terminal of the battery is going to exert a force F on this electron. So force causes acceleration. So this electron will be accelerated towards end A. But what is going to happen? It is going to be colliding with the positive ions which are going to be in their way, right? So all these positive ions, there are lots and lots of positive ions in its way. So this electron, after gaining a lot of speed, it is going to collide with this electron, sorry, the positive ion. In that collision, in that process of collision, it is going to lose its energy. So now that accelerated electron, when it received the energy from the battery, it lost some of its energy in form of the heat energy while the collision. Due to the collision, it will change its path. Now it will move in this particular direction, and again due to the force, it is going to accelerate, but again due to the collision, it is going to lose some of its energy in form of heat energy. Again due to the collision, it will change in its path. It will be accelerated towards end A. It will gain in the speed, but again due to the collision, it is going to lose some of its energy. The similar process is going to happen, and the electron keeps on colliding with these positive ions, and then finally it is going to reach at end A. So after lots and lots of collision, it is going to reach at its end A. So this collision is the basic cause of the resistance. So we want these electrons to move freely inside the rod without any kind of collision, but that is not going to happen. So these collisions are the basic reason of the resistance. Second reason for the resistance is their internal collision of the electrons, because this is not a single electron which is actually going to move. So there are crores and crores of electrons which are moving together. So their internal collision also leads to the resistance. Let's understand that resistance is a scalar quantity. Its SI unit is ohm, and we represent it by this symbol. So this is the symbol for the resistance, and this is basically fixed resistor. Resistor means any substance that has resistance in it. So a metal rod can also be referred as a resistor, right? Resistance is a property of a substance to oppose the flow of current, whereas resistor is a real thing, right? And then there are few apparatuses or few instruments whose resistance is variable, right? We can change its resistance. So this is the symbol for variable resistance. And then we have one special case with a variable resistance with a jockey which can slide over. This is known as rheostat. Now rheostat, and it's a type of variable resistance whose resistance can be changed, right? So variable resistance can be of many types, but rheostat is a special kind of variable resistor. Now let's look into the factors that affect the resistances. Let us understand that how the length of the conductor affects the resistance. So let's practically understand this. If this is a shorter wire, and then you have a longer wire over here, like this. So of course, the shorter wire is going to have lesser number of positive ions, like this. And here the longer wire is going to have larger number of positive ions because of the more material or more matter added to it. Correct? Now, if the free electron passes through this, then it will have to suffer less number of collision, and then it will come out. Whereas here, since there are larger number of positive ions, so it will have to collide with larger number of positive ions, and finally the electron will come out of the conductor. So larger the length, larger the positive ions, larger the number of collisions, so more is the resistance. So we can say that R proportional to N. Second, the cross-sectional area. That is A. Now, which cross-sectional area I'm talking about? So suppose this is the length, right? This is known as the curved surface area, correct? But this is known as the cross-sectional area. So we are supposed to discuss about the cross-sectional area, because when you connect a conductor across the circuits, the electrons will be entering through this cross-sectional area. They will be actually encountering this cross-sectional area, and when they will come out of the cross-sectional area. The electrons, they do not pass through this curved surface area. So we are only going to discuss about the cross-sectional area. So you can just imagine that if the door is small and in a room, if there are 10 people and if the door is open and all 10 people they rush through the door outside, then the number of collisions between all of them will be very large, right? They won't be able to go out of the small door very easily. So because there is a lot of collision between them. In the same way, when the cross-sectional area is very, very small, larger number of electrons when they try to enter, there is a collision between them, and their internal collision also leads to resistance. So you can say that that if the cross sectional area is very small, then since lot many electrons when they try to enter, there is an internal collision between all of them. So smaller is the area, more is the collision, so R proportional to 1 upon A. This is the second factor, right, that affects the resistance. Now, there is also the third factor, that is the temperature. And you can just imagine something like this, that if the temperature of a rod increases, then what is going to happen? The free electrons, they will be moving faster because due to the increase in temperature, their kinetic energy increases. So when they move very fast, the chances of collision become still more prominent. And when the chances of collision and the collisions increases, the resistance, of course, increases. Okay, but when we do any kind of experiment with respect to the resistance, we do it in a closed vacuum where the temperature is constant, right? So we know in maths that if R is proportional to A, or let's say X is proportional to A and X is proportional to B, then X is also proportional to the product of A and B. In the same way, here the resistance R is dependent upon two factors we have studied, R proportional to L and R proportional to 1 upon A. So if I combine them both, R will be proportional to L into 1 upon A. So R will be proportional to L upon A. Now, if you want to remove this proportionality sign with is equal to sign, we'll have to put a constant, that is rho. Now, this rho is known as resistivity, or it is also known as specific resistance. So it will be discussed later, right? What is specific resistance and all the stuff. But right now we have obtained a very important formula about the resistance, that is rho L upon A. Of course, the temperature also affects the resistance of the material. So you can say that as you increase the temperature, the resistance of the material increases. But please understand, here we are only talking about conductors, right? So this is the main formula of the resistance. And now let's discuss about few of the problems related to the resistance. Okay. So suppose I may give you, this is the first question, that the length of the rod, suppose this is the rod and it has length L and the cross-sectional area is A. And by the way, this is a metal rod, right? So what is its resistance? So we should say that R is equal to rho L upon A, correct? Now, please understand, I have not discussed about the resistivity, but please remember right now that resistivity depends upon temperature and material. So when you will cut the rod into half, or when you will slice the rod into 3 parts, or when you pull the rod, you are not changing the material. So the resistivity remains the same. Correct? Okay. And please do not confuse that this symbol rho is for the specific resistance or resistivity, not for density over here. So now the first question says that you are cutting the rod into 2 equal parts. So now this rod is divided into 2 equal parts like this. This is the first part and this is the second part. Now what happens when you chop off this rod into 2 equal parts? The length reduces to half and the cross-sectional area remains the same, right? And let me call the resistance of this rod as R dash. So now the new resistance R dash is equal to rho, because the material is not changing, L by 2 upon A. So this will be rho L by 2A, and since rho L by A is our old resistance, the resistance of the previous rod, so R dash is equal to R by 2. So very simple problem, that if you chop off the rod into 2 half, the individual resistance, they become half. So now let's move to problem number 2. Now in problem number 2, you are given a rod like this, And now you are going to slice the rod into two parts, but in the following way, not from the top, like this one. Correct? So the cross-sectional area will be half compared to the previous rod. So something like this is what we are anticipating. So no change in the length, but the cross-sectional area becomes half. So now the old resistance R was equal to rho L by A, but here the new resistance R dash will be equal to rho, then L remains as it is. Here the cross-sectional area becomes half. So that means this is 2 rho L upon A, so the resistance becomes twice of the previous resistance. It is because you have reduced the cross-sectional area, so the internal collision between the electrons will increase, right? So the resistance doubles up. Now the third problem is something like this, that you have a rod and then you are going to chop off this rod into two halves and you are going to place it one over the other. So something like this, you are cutting this rod into two parts and then you are going to place the individual sections on one another. So like this. So in this situation, the length of the entire conductor becomes half, but now this cross-sectional area through which the electrons were previously entering, like this, was A. Now the electrons can enter through a larger cross-sectional area that is twice of A. So here the resistance is equal to R is equal to rho L by A. The length of the conductor is L, which is being chopped off into half, but the area of the cross-section is now double. So here let me call the resistance as R dash. So R dash, that is equal to rho, since we are not changing the material, the length becomes half and the area becomes double, right? So the R dash is equal to, so the overall resistance decreases L by 4A, and rho L by A is R, so R dash is equal to R by 4. So the overall resistance decreases by 4 times. I hope you are getting these kind of problems, right? Fine. Now the third problem is you are having the wire and then you are cutting this into half like this, and then you are placing both the rods. We are not changing the length, but the cross-sectional area now is now reduced because this is A, this is L. Correct. So here the length remains as it is, but then you are connecting the rods end to end like this. So now the length becomes double and the cross-sectional area reduces to half. So in this situation, R was equal to rho L by A, but here it will be R dash. Please do not use the symbol R because it is being used for the previous resistance. So R dash is equal to here rho, then 2L, the resistance will definitely increase, and A by 2. So this is equal to 4 rho L by A. So the new resistance R dash is equal to 4 times of the previous resistance, something like this. Question number 4, you have a rod. Now you are not cutting the rod, right? You are pulling this particular metal rod from both the ends like this. So you are pulling it from both the directions. So if you will increase the length, the cross-sectional area will reduce. In the cutting case, it was not like that. Now, since you are pulling the rod, the cross-sectional areas will decrease. And what is going to happen? The length is going to increase. So something like this is going to happen. So the length is being doubled, right? In the problem, it is given that the earlier length was L. Now the new length is twice the previous length. But now you will have to figure out that what will be the change in the cross-sectional area. So earlier the cross-sectional area was A, let me call this as A dash. But please understand this, that density is equal to mass upon volume. When you stretch, you are not changing the mass. The material remains as it is. So suppose if it is a copper wire, you are just stretching the copper wire, so no change in the density as well. So as per this, the volume should not change. Now, since these wires are cylindrical in nature, volume is equal to area multiplied by length. So if you double the length, what should happen to the area? It should get half. Then and only then the volume will remain constant, because volume is equal to area multiplied by length. So if you double the length, the area should go half, and 2 will get cancelled, and that's why the cross-sectional area reduces by half. Right? So if you triple the length of the conductor 3 times, then the area will be reduced by 3 times. So in this case, the area will be A by 2. Now let's find the new resistance R dash, that is equal to rho, no change in the material, so resistivity remains as it is. L, now we have 2L, and it will become A by 2. So R dash is equal to 4 rho L by A. So that means the resistance becomes 4R. One last problem on the resistance is the following. So suppose you have a conductor whose radius is R. So definitely we are going to talk about the cross-sectional area, right? The radius of the metal wire is R. The length is L. So the resistance is equal to rho L upon A, where A is the area of the cross section, which can be written as pi r square, because it's a circular cross-sectional area. Fine. Now, if in the question, if it is being asked that suppose you double the radius, so the radius now becomes 2r, and the length remains as it is, like this. Then what is the impact on the resistance? So now the resistance R dash will be equal to, since we are not changing the material, so that is rho, then no change in the length, so L, and now here pi 2r the whole square, because we are doubling the radius. So this will be rho L upon 4 pi r square, and this part, that is rho L upon pi r square, is equal to R, the previous resistance, divided by 4. So the overall resistance decreases by 4 times as compared to the previous resistance. Now, one more point I want to just add over here is that if the substances have a lot of resistance, those substances are known as, you can say, bad conductors or insulators. But the substances which are having very, very less value of resistance, they are known as good conductors. Now, it is practically found that the number of free electrons is found very large in number in case of conductors. Correct? So the current carriers are the free electrons, and they are found in lot many quantity in the conductors, whereas in the insulator, the amount of free electrons is very, very negligible. So there is no one to carry the current from one area to the another, right? So we would be seeing the next part of the video, and we'll understand Ohm's law.